So in last lesson or so, we were looking at geometric sequences. So we're looking at exponential modelling in general, and we see that we can use exponential modelling to show rate growth, patterns of rate growth, I suppose. And the two different models are exponential functions and geometric sequences, very similar to linear functions and arithmetic sequences and series. And we wrote some notes down about geometric sequences last time, and those notes are there now. We didn't write too much because we were doing other stuff as well. There are some examples of geometric sequences there on slide 2. But now I need to correct the record a little bit. Not that there's anything wrong with what I've written there, but I don't know if you remember or not, but I said to you that for growth, R has to be bigger than 1, and for decay, R has to be less than 1, and that in general, R has to be greater than 0. Do you remember me saying that? I was being a bit of a numpty at that point because although there's nothing particularly, well, no, there is something wrong with what I said there, and that is that all of this is true when you have an exponential function, right? And the reason why is because if I have a fraction raised to a negative power, then it actually doesn't exist, which is a bit of an awkward thing for a function. So that's what we're talking about, fractions or negative numbers. So that's a problem. However, in a sequence, it's not a problem. What happens in a sequence is that, let me just pick a really simple one, like 3, negative 3, 3, negative 3, etc. To get to each term here, I'm multiplying by negative 1. So I can generate a sequence quite happily. That's no dramas at all. But in terms of if I was graphing it, then I could graph, I'd be graphing 3, then negative 3, then 3, then negative 3. But then there'd be a lot of confusion of what's happening in between here. I won't go into too much depth, but I'll just say that's why your graphics display calculator falls over. That's why your Desmos falls over, because between 3 and negative 3, there's a whole lot of fractional values, some of which work and some of which don't. I won't go through any more than that. I might do it when we get back to exponential functions. But yeah, there is this sort of issue. The reason why it works with sequences is exactly why sequences are sometimes better than functions. Sequences, remember, deal with counting numbers. N equals 0, so n equals 1, n equals 2, n equals 3. Whereas functions deal with everything in between there as well. 1, 1.1, 1.2, 1.3, and then also 1.11, and also 1.1111, and so on. So there's an infinite number of little numbers between 1 and 2. Functions are good for that. But then something like this, it's not. So I need to correct the record a little bit. I was thinking too much about exponential functions when I said what I said. So I just wanted to add to that to note that if R is less than 0, we have, oops, sorry, I didn't realize that was going to be, we have an alternating sequence. Or oscillating is sometimes what it's called as well. Oh, double L, I think. Okay, so it kind of just goes sort of positive and negative and positive and negative and positive and negative like that. It's just got an oscillating pattern. Okay? It's not to be confused with an ocelot pattern, which is just a piece of fabric with ocelots all over it. It's different. This is oscillating and going upwards, up and down, up and down. So a sine wave is oscillating, for example. But again, it's discrete, so it doesn't have all those values in between, which is why we can't treat it like a function. So if r is less than 0, we have an alternating or oscillating pattern. So if I was trying to not be technical as well, but the truth is that I kind of have to do this. Do you know what that symbol means? So I don't want to write too much down. Who knows what that means? Who's seen that kind of symbolism? Do you know what I'm talking about? See how I've put bars around the R?
Oh yeah.
They weren't there before. Absolute value. And what does absolute value mean? Always positive, or the sign is stripped out of it. Yeah, either way. So when it says the absolute value of R is greater than 1, it basically just means anything above 1 or below -1. And the absolute value of R being less than 1 means everything between -1 and 1. In other words, it's a decimal. It might be a positive decimal or a negative decimal, but it's a decimal. A fraction. Is that okay? Does that make sense? Okay, it's shorthand for saying that. So I don't really need the R greater than 0 bit now. But do note that, if R equals 1, remember what I said? When R equals 1, it's starts with trivial. If R equals 1, it'll just be the same number over and over and over again. So it's trivial. And if R equals 0, it's dodgy as well. Alright, so that was the geometric sequence with examples. What I want to focus on in today's lesson is this stuff here. I've got 3 examples, one of which is sort of done twice, and you'll see why in a second. And it's about finding the common ratio, and then from the common ratio, being able to, oops, I've actually got the working out there, I didn't mean to. I always do the working out beforehand just to make sure I haven't chosen a dumb example. So whenever it doesn't work out, you'll know that I haven't prepared properly. So we're going to start with example 1 here, finding the common ratio. So, oh man, thank you. Awkward moment, isn't it? It's just better if we sort of evolve it as we go along, that's all. Okay, I'll just zoom in, so we might as well, since we've only got one screen to look at. So the common ratio R. So R is the value, remember, in the general term, where we multiply the next term by R to get the term after that. So it's called the common ratio, or R. So 3 minus 6 and 12. Now, of course, for a lot of the time, it's kind of obvious by inspection. You can look at it and say, oh, yeah, I have to multiply that by -2 to get -6. Done. Does that work for the next one? -6 times -2 equals 12? Yeah, it works for that too. So by inspection is basically, it's okay. I'm not too fussed by it. But in some instances, particularly when there's algebra and stuff, it's good to have a formalised process. And I'm sure that there are some students in this class who really like a formal process rather than just always doing it by feel. So this is how we do it. We say R is equal to, and then I pick any 2 consecutive terms. What does consecutive mean?
Next to each other.
Yeah, next to each other. So in other words, I could choose first term and second term, or second and third term. I'm going to choose the first and second because they're almost always smaller numbers. So I go -6 divided by 3. Get used to writing things in fractions. That's how we should do it in more grown-up maths. And that equals -2. Done. That's how you work out the common ratio. Don't do this bit, but just to prove to you, 12 divided by -6 is also -2. So it doesn't matter which 2 consecutive terms you choose. If you know it's a geometric sequence, then you pick those 2 consecutive ones and divide them out. So we've got R equals -2 there. We can now write the general term, 3. Now, are you okay with this notation? I have used it before, but I just want to make sure everyone gets that notation okay. I like it because it means we don't have to worry about multiplication symbols making it more messy. So you might see in certain textbooks 3 multiplied by -2 to the power of n minus 1. It's the same thing. I just got rid of the times symbol. You don't need it. On your calculator, it would look like this. It's all the same thing. Is that okay? please ask me if you don't get my notations, because I have a particular way of doing it, and if you don't get it, it really can be a stumbling block. This is what you can't do though. Okay. Don't. And then, don't do this. What's the difference?
It's 2 to the n times.
Yes. Did everyone get that from Zoe? What tells us, what basic grade 7 mathematical principle tells us that that's 2 to the power of negative 1, 2 to the power of n minus 1, then made negative?
Bondas, Bendas, Pendas, whatever you call it.
Botnas, Bondas, Bidnas, Pendas, Pendas, Bendas, Bonsa, whatever you want to call it. Yeah, because addition and subtraction from left to right, or subtraction and addition from left to right, doesn't matter. So we always do powers before we do negative subtractions, for example. Well, in this case, it's multiplication. Okay, so negative 2 to the power of n minus 1 means repeat multiplying minus 2. That's correct, we want to do. This one means repeat multiplying 2, 2 times 2 times 2 times 2, and then make the answer negative. So these are substantially different. And if you put, if in your GDC, you put negative 2 to the power of 3, oh, that's a bad choice, Richard.
It's
Come on, man.
anyway.
You can tell me later why it's a bad choice. If you put into your calculator negative 2 to the power of 4, you will get negative 16. But if you put negative 2 to the power of 4, this is going to be weird on the video, isn't it? I've just said the same thing twice. If you do negative 2 to the power of 4, you'll get positive 16. There is a difference. 2 to the power of 4 is 16, make it negative, negative 16. Negative 2 to the power of 4 is negative 2 times negative 2, which is positive 4, times negative 2, which is negative 8, times negative 2, which is 16. Okay? As a general principle, and you'll need to know this for geometric sequences, and you should know it already, if you raise a negative number to an odd power, the result is negative. If you raise a negative number to an even power, the result is always positive. So negative 2 to the power of 20 is going to be even. That is going to be positive. Negative 2 to the power of 19 is going to be negative. Okay, that's a general principle. And if you're not too sure why, I'll explain. Oh, I erased too much. I'll explain why personally to you. Okay, so don't do that. Always put brackets around it. And I just do it for positives as well, because I think it looks neater anyway. Okay, zooming out, let's have a look at a couple more examples here, and then I'll let you get on to work. Example 2, 27, 9, and 3. So this is pretty much the same thing, so I won't waste your time by belabouring it, but you go 27 divided by, oops, wrong, 9 divided by 27, and then you cancel down to get 1/3. Done.
No.
Of course you could write 0.3 recurring if you wanted to, but there's no need to. I find it a bit tedious to do that unnecessarily. So leave it at 1/3 and that's absolutely fine. P.S. This is an example with a descending sequence where I might just choose the other two terms because 3/9 I can clearly see as 1/3. The smaller numbers are all kind of a little bit easier to see where we're headed with them. So you can choose any two consecutive, remember? So therefore, u sub n is the first term multiplied by the ratio to the power of n minus 1, and we're done. Now what I'm going to assume is that if I ask you to find the 10th, like with a calculator, PS, if I ask you to find the 10th term, you'd be okay with that. Because it's really just 27 times a third to the power of 9, done. You've done arithmetic sequences and stuff, so I think you should be okay with that. Okay, example 3. This is where it gets a little bit more interesting, I think. It's one of those ones where you don't have the initial term or the ratio, but you need to somehow work it out. Now, if you remember, the way we did it with arithmetic sequences is we did it by simultaneous equations. We use a similar technique with this, but it's actually easier. And it goes a little bit like this. This is the long version. I'll give you the short version in a second. But it kind of starts off similarly. So we go, I know U2, apart from the band, and it's equal to 6, but it's also equal to the first term multiplied by r to the power of 1. Okay, so I'm using the idea that in a geometric sequence, it's u sub 1, r to the power of n minus 1. I also know u5 is 162, and that's going to be u sub 1 to the power of 4. Yeah. Okay, now we can't do simultaneous equations here, but there's this neat little trick that you can do. Watch this. Therefore, u sub 1 r to the power of 4 divided by, this is why I was getting you to do it as fractions, divided by u sub 1 r to the power of 1 must equal 162 divided by 6. Yeah? So what I'm doing is I'm creating a ratio of the two terms. So this is a ratio of the fifth and the second, and this is a ratio of the numbers there. Okay? So why do that is because always, you'll end up cancelling out the U1s, the first terms, and then you've got r to the power of 4 divided by r, which will give me r, oops, I don't know why that should pass, I don't know why, which will give me r cubed. Does that make sense? Just a reminder that basically we subtract the two powers away from each other, so 4 minus 1 equals 3. And I believe 162 divided by 6, carry 1 and 7, is 27. And therefore, r must equal 3. What do you think? Is that okay? Cool. So now that we've got r, we've got to work out u sub 1, and then we've got to put it all together. And this is the long version, so I haven't left myself enough room, unfortunately. But let's just give it a go. What was I going to say? Should I say it now? No, I'll say it later. Okay, so we've got r. So I'll go back to my simplest one, which is u sub 2, and I can go, therefore, u sub 1 times 3 is equal to 6, and u sub 1 is equal to 2. Oh, that was alright, wasn't it? That wasn't too hard. And therefore, u sub 10 is equal to 2 multiplied by 3 to the power of 9, which is equal to, someone get there before me, 300 and something, right? No one's reaching for their calculator. Okay. I don't mind actually, because unfortunately, if you're watching this video, you're not going to see me switch over to my calculator. But if I fire up a new calculator, then I can go to, thank you, I'm just going to do it so you can sort of turn your calculator. 3, and to the power of is just that button there. So 3 to the power of 9, return 39,366. I was out by a factor of 10 there. 39,366, and we're done. Is that okay? Do you want to see the short version now? So, people who like to follow formulas and processes will love the long version, and there is nothing wrong with it. It is perfectly acceptable. Please don't think there's anything wrong with it at all. So in example 3, the short version, so if that was the only version you used, I reckon you'd be solid all the way through this. U sub 2 is equal to 6. I've got U sub 5 is equal to 162, and I'm after U sub 10. Okay, so the shorter version is a bit like this. It's basically saying, how do I get from U sub 2 to U sub 5? Well, I'd have to multiply once, twice, and 3 times by r. So using your logic, you can see that it would be r cubed. Yeah? Because it's got to be, to get to u sub 3, I multiply by r. To get to u sub 4, I multiply by r once more. And to get to u sub 5, I multiply by r once more again. Okay? So 6 multiplied by r cubed is going to be 162. Does that make sense? I'm starting with 6. I've had to multiply by r 3 times to get there, and my result is 162. Now I divide both sides by r, by 6, sorry, and I'll get 27, and then I'll cube root both sides to get r equals 3. Then the rest as per long version. Oh no, actually no, there is one more. There's one more shortcut I forgot. Okay, so we've worked out that r equals 3 just by following our logic. Anyone got any questions about that? Well, the next thing we can also take into account is this, right? To get to the 10th term, I need to go from the 5th term and go r times r times r, 5 more r's, right? So that means, therefore, u sub 10 is going to be the 5th term multiplied by r to the power of 5. Is that okay?
Wait to the formula.
Because the 5th term is 162, so I'll need to multiply by r to get to the 6th term, then another r to get to the 7th term, then another r to get to the 8th term, then another r to get to the 9th term, and then another r to get to the 10th term. So repeated multiplication 5 times gives me r to the power of 5. So it's going to be 162, and then another 5 multiplications of r. Cool. Which is equal to 162 multiplied by 3 cubed, which is equal to 39,366.
3 to the 5th, not 3 cubed.
Thank you. I'll fix that up. Should be that. 39,366. Confirm on your calculator that it should be 162 times by 3 to the power of 5.
It works.
Should be 39,366. Thanks, Eric. Okay, so does that all make sense to everybody? So long version or short version, it's up to you. The benefit of the long version, so this version, is that it's just repeatable. You can just do exactly that every single time and it will work. The benefit of the short version is that it's short. The negative of the short version, it's not really a negative, but you have to think each time. You need to make sure you're thinking about what's going on. Okay, I will stop the video there, and that will be uploaded in just a moment to Google Classroom along with these board notes.